Okay, we'll go ahead and get started. So as I just wrote there, your lab 3, your mesh and nodal analysis, where you had the 2 parts, we did it over 2 weeks. One part you were doing and analyzing that in theory using a computer program. And the second part you needed to do that by hand using our Cramer's rule. Because I did not actually post the lecture recordings and the lab recordings to the correct year, it got posted 2019 circuits instead of 2021. Oh, jumbled together in Canvas. I have now fixed that. They should be published to our courses from the 2021 versions. I've extended the deadline for your lab for that to Friday at midnight. So use that to your will. If you have questions on that after lecture, please feel free to ask me or during lab this week. Lecture 5 from last week, the Thevenin and Norton analysis, which we'll be doing in lab this week, also should now be posted. The recording from that was not posted to the correct year, so I apologize for that. Today we will be talking about op amps, which are, op stands for operational amplifiers. And they are my favorite circuit elements. Just as a note, we will be doing them a lot. You will also see a lot of them in sensing and measurement, the next course you take from this as well. So just as warning, they're very useful circuit elements that we'll get into. Okay, so what is an op amp or an operational amplifier? I call it a magical circuit element because it can do some cool things for us. It allows us to do math with circuits. They can add, subtract, multiply, or divide. And so if we can do math with electronics, then we can combine different signals or different voltages at points together the way we want to. So we can multiply to make a voltage larger than it was before. We could add 2 voltages together or subtract them to get a difference between voltage. And that's very powerful for signal analysis or for something you want to measure and then process so that you make it larger, smaller, compare it to something else. Anything you're comparing to that, we can do that with op amps. How do op amps work? Is they act like dependent sources. Remember I said I won't actually make you do dependent sources. We did see an example of that last week. I won't test you on them. But dependent sources are current or voltage sources that change their current or voltage output based on an input. Okay, so they are a unique beast. We're not going to get into them as actually drawn as a dependent source, but it is useful to have in the back of your mind that that is how they work. We're going to get into them by just using some set rules for how they can work in a circuit. And if we follow those rules, we can use them to our advantage. What do op amps look at? Like, I call them little 8-legged spiders, or they kind of look like some sort of Star Wars robot for something. In real life, this is one. Again, circuit elements are tiny in general, right? But he's got 4 little metal legs on one side, 4 little legs on the other. And in a breadboard, we tend to put them what's called across the gap in your breadboard, from where it goes from 5 pins on one side to 5 pins on the other. And we'll see that we put them across this gap so that the pins on one side can get a different voltage than the pins on the other side. Remember, your breadboard connects a group of 5 pins horizontally, if it's not the power rails, together, but not across the gap. These 5 pins can be a different voltage than the same row across here. Okay, so that's what they look like in real life. They have a little notch or a dot to identify the top of them because then their pins are numbered accordingly from that. In a circuit diagram, though, ironically, we don't draw them with 8 legs. I guess it's just too many legs to draw. And a lot of the time you aren't really doing anything with all of those legs. We tend to draw them as a triangle instead, with a minus sign, a plus sign, and then a point of my triangle that gets no sign from it. How this relates to actually my 8 legs is, see this overlap of my triangle on my 8-legged diagram here. The minus sign is what we're going to call the inverting input. We'll talk about why it's inverting once we do a derivation of it with a problem. The plus sign is what's called our non-inverting input, which is a bit like calling something, like unsweet tea. You're naming it by what it's not. It's not sweet. This one's not inverting. And then the side of our triangle that doesn't get any label is the output of our op amp. So we put things into our op amp and we get things out. And again, normally what we put in, we want to do some math on: add, subtract, multiply, divide, and then our output is the result of that math. Okay. There are in reality 8 pins though. We really care about these 3 the most when we're calculating them in theory in a circuit, but in real life, you may have to care about the rest of them. So 2 other extra pins to note are one on this schematic that says V minus and V plus. I'm going to actually use a different color here so I don't confuse them. Let's use. Yeah, let's use red. These are called our power rails, or the power supply for your op amp. They are not the same as the minus and plus here. So this is not, for example, the inverting input. And that can get confusing because it looks like, oh, it's a voltage minus. That's my voltage right here, and that's not true. Op amps, I say, are magical. They allow us to do math, but they don't allow us to do math in electronics without giving power to them. So just like your phone is very powerful, your laptop's very powerful, right? TVs, any electronics, none of those things are powerful unless you give them energy, right? A power source. You've got to plug in your laptop or at least charge its battery. Same thing with your phone. Our op amps will only work to do math, give them power at these 2 points. In this particular type of op amp. There are different types of op amps that only want power at 1 point compared to ground. This one actually wants a positive and negative power. We don't often see them in a circuit diagram, as we'll see, but some of the time you do, is an extra line going up. That's your positive voltage supply. And an extra line going down, which is your negative voltage supply. So that negative voltage supply would be what I attached to pin number 4 here. Their pins are numbered down 1, 2, 3, 4 on the left-hand side from their notch. So this would be 1, 2, 3, 4. And then up on the right-hand side, 5, 6, 7, 8. Don't ask me why they go up in numbering on the other side. So this would be pin 4. This would be pin 7, one coming off of here. Our inverting input would be pin 2. And our non-inverting input would be pin 3. Okay. So how we analyze an op amp in a circuit, because they're going to be different. They're not a resistor. They don't behave just like a resistor. They're really a dependent source, but it's easy enough to analyze them if we follow these rules. You don't really have to memorize these rules, but it is very helpful to get familiar with them. Again, I don't really require you to memorize things in this class. You can look back at notes, but some of the time, the more familiar you get with things, the faster you can do something without having to look up these. So by the time we do a lot of op amps at the end of the semester, it would be helpful to be pretty on top of remembering these rules. Rule number 1, no current can enter the op amp at the inverting or non-inverting inputs. So my inverting input is this guy. If I have anything attached in a wire to him, or in real life, anything in the row that goes with that pin, which is pin 2, that current on that branch of wire has to be 0. Because current entering really means current trying to go into my op amp this way. It's the same as current leaving, right? That would just be a negative current. So it really can't enter or leave. It's just more commonly phrased as enter, since these are called inputs. My inverting input, anything I attach, here's my non-inverting input, also has to have a current of 0. Okay. Practically, they do this because there's a very, very large resistor that actually attaches to these inputs. And if I have a really large resistor going in between them, then we know Ohm's law, right? Delta V equals IR. If R is really large, you have a set V. What happens to your current? with a really large resistor, what happens to the current, assuming voltage stays the same? Yeah, then it becomes really small. So if you make that resistor impractically large, normally we're talking about hundreds of mega ohms, 10 to the 6 ohms, then practically this current is going to be so small that it's practically zero. And we like to assume it's actually zero. In real life, it may not really be that, but it's going to be really small. Rule number 2, op amps can amplify a voltage to infinity. So what does amplify mean? It just means multiply. And what voltage am I multiplying? I'm talking about my input voltages, or the difference between them. So I have an inverting input and a non-inverting input, as we'll see. So we said they're magical, they can do math. Part of that math is they can multiply, make a voltage larger. In theory, they can make it larger up to infinity. So if we're analyzing them on paper, we like to assume what can come out of this at its output, right here, could be up to infinity. So if I measure a voltage out on that wire, it could go up to infinity. In real life, nothing goes up to infinity, right? Infinity is a nice thing if you're a mathematician, but not really so much if you're an engineer, because nothing's ever going to get that, right? What's more limiting in reality than the fact that I can't actually get to a number that's infinity, it's just a limit, is that the voltage at my output, what comes out here on this wire, cannot exceed the voltage supplied in the power supply. So these power rails are our power supply, negative voltage supply, our positive power supply. If I make this, let's say, back to red, sorry, if I apply negative 15 volts to pin 4, and I apply positive 15 volts to pin 7, that's going to be a very common voltage range that we use. Then in reality, what comes out of my op amp cannot be any higher than positive 15 volts and can't be any lower than negative 15 volts. If I were to graph, then my voltage out on my y-axis versus my voltage in that I apply from one of these inputs, or the difference between those inputs, what would happen is if I get to V out's my y-axis, negative 15 volts and positive 15 volts, and I will reach an asymptote at each of those. So it might look from here like I could keep multiplying to get V out to forever, but once I get up to positive 15, it's going to flatten like this. And when I get down to negative 15, it's also going to flatten. So in reality, it's really important to know, and I've been guilty of this myself, is we'll design a circuit to multiply by something we want, think we can multiply by it, and then realize we're not giving it enough power to actually create that voltage. It can't pull a voltage from nowhere. So if you don't give it power higher than that, it can't make a magical higher voltage. Okay. So you're limited by what you power it here. A lot of the time for us in our very small circuits, positive and negative 15 volts is enough. But if you're really trying to get a higher voltage of something, then you need to give it a larger power supply. Rule number 3 for our op amps, and these are what are called ideal op amps. Again, ideally no current enters. In real life, where things aren't perfectly idealized, then maybe a little bit does. It's just a large resistor, and ideally I can get to infinity. In reality, I can't. Rule number 3, inverting and non-inverting inputs will be held to the same voltage if a feedback loop is present, and there should always be a feedback loop from the output to the inverting input. Technically, you can make an op amp without one, but I will never give you one, and you shouldn't make one without it. It's just a stupid exercise if you don't. Okay, so here's my op amp. It's a triangle. I get my inverting input has a negative sign, my non-inverting input has a positive sign, and here's my output. Feedback loops always go from your output, they measure what you create in your output, to your inverting input. It matters which one, because you're kind of comparing it to your input. So I could have a loop just like that, that's just wire that connects my output to my inverting input, or I could have it with something like a resistor in there, or as we'll learn later, other circuit elements like capacitors or things. If you think about feedback in terms of a thermostat, it's really hot in Cincinnati now, at least if you're in Cincinnati. And if you're trying to set the thermostat for your house, what it's doing is saying, okay, I've set it to 76 degrees maybe, and it has a plus or minus 2 degree range that it's okay with that. If it goes above 2 degrees over my set point, so from 76 maybe to 78, I measure that on my output because I'm sensing my temperature, and I compare it to what was my desired input, wanted it to be 76, and comparing it means I'm subtracting, or I'm taking the difference between those two and saying, hey, is that more than 2 degrees off from what I wanted? Maybe you only want it within 1 degree. There are actually, if you've never played with that in a thermostat in your house, there should be settings for how far off you can be from your set value, because nothing's perfectly 76 degrees, right? Maybe it's 76.5 and that's okay. Maybe it's 75.5. They're always settings, but they're comparing your output, in this case of a thermostat actual temperature, to your input, and to compare you subtract. So it's using our inverting input from that. In our case, it's taking the voltage at our output and comparing to the voltage at our inverting input. Okay? So you should always have some path. It may just be a wire, it may be a resistor, it may be a whole bunch of resistors in parallel. It may be other circuit elements that we'll get to later, like capacitors. It can be all kinds of things, but there should be some path for a current to go from my output to my inverting input with op amps. If that's true, so if there's a feedback loop present, if a feedback loop is present, then it means my inverting and non-inverting inputs will be held to the same voltage. So that means if I have a voltage, let's call it voltage A here, and my inverting input on this wire, then if I have a wire coming from my non-inverting input, this will also equal VA. So it seems like, oh, well, one should be negative and one should be positive from the labels. They don't actually mean that. They mean in practicality, what happens is an output when you attach things, as we'll see. But in real life, you don't actually care which one is inverting or not inverting a lot of the time. They'll have the same voltage. So if VA here is 2 volts, then this is also 2 volts at my non-inverting input. It's not negative 2 volts or plus. That's very powerful because it means if you know the voltage at one input, then you automatically know the voltage at the other. Okay. Rule number 4, infinite current can enter or leave my op amp at the output. So again, my op amp is the one, my output is the one that doesn't get a negative or a positive sign. And while I have no current here, right, no current goes into my inputs, that was rule 1, I can have current leave here. So it's a little funky in that normally that means there's another path for where that current can go that doesn't have to feed back into there as well. Again, in reality, infinite current probably isn't going to happen, but it's definitely going to be some amount of current that isn't zero, where our inputs don't have any current in practicality. Also note, we've learned mesh or nodal analysis. Just for an interesting poll, how many people prefer mesh and how many people prefer nodal? If you could type in the chat, what's your favorite? We'll do a popularity contest between mesh or nodal analysis for analyzing a circuit, because really you can often use either. Again, they're alternate methods. Yeah, so I'm getting most people use mesh. Again, it's nicer when you don't have fractions. I don't know why we don't like fractions, but we don't. Unfortunately, you tend to not be able to do mesh with op amps because mesh requires you sum up voltages in a closed path, right, along a loop or along a mesh, and you won't have a closed path. You'll have unknown things that go on inside the triangle that is an op amp and the mystery that lies within them. Okay. You will learn in sensing and measurement. If you're interested, let me know and I can tell you more about what is actually inside an op amp. There are actually a whole bunch of circuit elements that are inside it that make it do its cool math abilities. But because you don't know everything that's going on inside, you can't make a closed path in a mesh. We're stuck doing nodal a lot more because we can identify single points or nodes and look at current into or out of. So that's why I make you learn both. I'm sorry if mesh is your favorite. It's probably my favorite too, but we're probably not going to be able to do it much with op amps. We can do nodal analysis. Okay, let's look at an actual circuit with an op amp, because otherwise it just seems like hogwash. So here's my op amp. It is a triangle. I have my non-inverting input, my inverting input. Do note, you can often flip these. You know, it just depends on how you draw your triangle. So right now I've put my non-inverting input on top. And this guy had the inverting input on top. You just have to pay attention to which one's which. Again, ignore my dots. That's just my circuit drawing program showing that there are connection points. But I have my inverting input. Do I have a feedback path here? Based on how we defined feedback. In this circuit, is there a feedback path? Yes, good, Miriam. What was the feedback path? Feedback goes from my output to my inverting input. Here's my output. I get a wire path with a resistor. That's fine. I can have whatever circuit elements it wants. And it goes back to my inverting input. I have that path. If I have it, it means by rule 3, the voltage right here on this wire at my inverting input has to be the same as here. So we'll see if we can find one of them. Rule number 1 said what? No current will enter my op amp at my inverting or non-inverting inputs. Again, that's not true of my output, but it's true of these guys. Current on this wire is going to be what? Or how could I calculate it? Based on rule 1, what will be my current on this wire right here? Zero. Good. No current. And it didn't matter whether you draw it into or out of, that current 0. Okay. My inputs. What about right here? Through Rn. Is this current 0? It'd be a yes or no. Ooh, good, Bennett. No. Why not? While the wire right here has no choice but to go into or come directly out of my op amp. If I'm current right here, do I have to go into my op amp? Where else could I go? If I go through Rn, good, McKinley, it has different path options. So where could it go? Yeah, it can go through RF instead. Okay, so you got to be careful if there are options in your path. That does not mean this one's 0, it just means this one is. So we're going to label it, and we're going to then derive what this means for the rest of our circuit. I'm going to call this I1. I don't know what he is, but he could be not 0. And I'm going to call this I2. We already dealt with current in this branch because he's 0. Here's ground. Let's do that. Again, as I warned, you can't do mesh. It looks like you kind of have a mesh here, but you have no idea what went on from here to here. So you can't continue that path. I don't really have a closed path here either, so I have no meshes. Again, don't know what goes on in between here either. I can do nodal, however. So if I do nodal looking at this node, what current goes into this node here based on how I've drawn my arrows? I just arbitrarily define directions of arrows for my current. What current's going in? Good, Quinn, I got I1. So I'm doing entering equals leaving. This is just my base nodal. I know we don't like float nodal, but it's not that hard. What's leaving? What's leaving the red dot? I2. Yeah. And you could write I2 plus 0 if you identify that this one's 0. Whatever floats your boat. I'm just going to write I1 equals I2, which again, really meant that the current through here had to then continue here. If you're fine with identifying that they're the same, then you don't technically even have to write it in nodal in this simple of a thing, but it does help. When we do nodal analysis, we label our currents, we do entering equals leaving. Then what do we change our currents into? What form do we write them in? I don't want to leave them in terms of I's. What do I like to change my current equations into? The hint, I like to use Ohm's law. Good, Anna. I like to do it as voltage over resistance, or really, again, delta V over resistance. And make sure you are doing it as delta V. It's a change in voltage. Oh, goodness. I've done this whole thing with like a black dot on my face and no one tells me. Okay. I1. Here's I1. Based on its arrow, again, because the arrow said it was entering, so I have to keep up with that sign with nodal. It goes from what voltage to what voltage, or what's going to be my delta V? If I rearrange this to say I equals delta V over R as I do for nodal. I'm going to write I1. It's delta V and then over what R? So it starts at, what's my voltage down here? 0. So I have to write it as 0 minus, and then it goes to some voltage up here that I don't know necessarily, just looking at this, but let's look at our other op-amp rules and see if we can figure it out. So we said if we had a feedback loop present with rule 3, that our inverting and non-inverting inputs will be the same voltage. So if I could identify a voltage here, I'm going to call this one VA and then this one VB, then it means VA has to equal VB. They have to be equal. What's my voltage at VA, at my non-inverting input? Remember, this is ground down here. What would I be up here? What voltage would I call that? Good, Quinn, VN, right? Because here's my voltage source, whether you made that 5 volts or 10 volts or whatever you did. And it means if this is 5 volts, then I'm 0 volts here, I'm 5 volts here, or I'm VN higher. So what's my voltage right here at VB? Also VN. Okay, so I go from 0 to what voltage? VN. Over what resistance? I'm writing as delta V over R. I went from 0 to my voltage right here at this wire is VN. Over what resistance? Good. Over RN. So the total way to write that, good, Benmet, is negative VN over RN. I always write it as, 0 minus that so I don't forget it. But otherwise, if you just say V over R, you think, oh, maybe it's VN over RN, and you messed up the sign. The sign matters. Okay. What about I2? He goes from what voltage to what voltage based on how I've drawn that arrow. So again, that arrow meant he was leaving. That's how I was able to say that. Good. He goes from VN on this wire to V out over what resistance? RF. Okay. I now have an equation that relates VN, the voltage that I'm applying kind of into this op-amp, in this case through my non-inverting input, and V out, the voltage I will get measured at the output of this op-amp. Let's rearrange it because I would like to solve for V out in terms of VN. As a hint, we should get this as a final answer. Let's prove that to ourselves. Again, we did this based on nodal analysis, looking at current at that node. So how am I going to solve this for V out? I want to get V out by himself. I'm going to erase that because he looks annoying. What's my first step to maybe get V out as a good? Multiply by RF on both sides. So what do I get on my left side if I multiply by RF? Left-hand side of my equation. See if you can work this out with me, because again, most people will mess up in this in the algebra, not in the actual rules of anything. Getting very close, I will have Vn onto then RF over Rn. Anyone see anything missing from that sign? Yeah, a big fat negative sign, right? Which is why you got to be careful with it. It was 0 minus Vn, so there's a negative there. Equals what? Now I have Vn minus V out on the right-hand side. Now how do I get V out on its lonesome? Just trying to isolate a variable. Well, there's nothing else really I need to divide by on this side. He's kind of over 1 now. I have Vn minus V out, though. I just want V out. I don't want this pesky Vn anymore on this side. I want him by himself. How do I get rid of Vn on this side? Subtract. Good. So if I subtract both sides Vn, I get negative Vn on this side. Again, I'm going to move them over. Subtract. And I then had negative Vn RF over Rn. What am I left with on my right-hand side? Good. Negative V out. Okay. Technically, I don't want him to be negative V out. I just want him to be positive V out. So now what do I do to my equation? Okay. How do I get him to just be positive V out? Multiply everything by -1. Good. Take this whole thing. -1. So negative gets rid of this negative, and I get positive Vn. Negative gets rid of this negative, and I get plus Vn onto RF over Rn. You could leave them like this, but I like to say, oh, I have Vn in both terms. So I'm going to pull out a Vn and factor it out. V out equals, if I factor out a Vn from this term, what do I get? It's like factoring out 3 from an equation or something. What do you get from this term when you pull out a Vn? I want to put in parentheses something. Yeah, good, just a 1. This would be like 1 times Vn. It's an implied 1. Plus, what do I get from this term when I factor out a Vn? Good, RF over Rn. What does this mean practically? I'm not even looking at my notes for this, which is probably dangerous of what I wanted to say. What does this mean this whole circuit did with my op amp to get a V out? It took a voltage in and it multiplies it, right? This whole thing is then multiplied, or you could write a big multiplied symbol here, by what? By 1 plus the ratio of RF. RF was this feedback resistor because he went from my output to my inverting input, over Rn, which was kind of an input resistor because he went kind of into our inverting input. So what does this mean practically my circuit does? He takes an input voltage. If I started with something I knew, like say it's 2 volts or whatever, and it multiplies it by this ratio. So if I want my circuit to do the math, that my voltage out should be my voltage in times 3, right? I wanted it to multiply by 3. Then what should the ratio of RF over Rn be? Good, 2. How can I make that ratio? Choose any values of resistors you want. So if I make Rn 500 ohms, then what should RF be? To still make it, this whole circuit end up multiplying my Vn by 3. 1,000 or a kilo ohm, right? In real life, there are limits into what's useful resistor ranges. We talked about that, like too low makes the current too high. too high would also make thermal noise. So again, we often are in kilo ohm ranges or at least hundreds of ohms. But in theory, if I don't give you limits and I tell you just make a circuit of this multiplied by 3, you could make RN1 and RF2. Just keep in mind in real life, 1 ohm and 2 ohm is probably not a practical resistance value because they're going to have ridiculously high currents and nobody likes that thing smoke and catch on fire. Okay, so why is V out equal to Vn times 3? Just an example of saying I want to do that. What if I want to do V out equals my voltage in? I want to take my voltage in and I multiply it by 5. Then what do I want RF and over RN to be? 4, right? What you multiply Vn by, this whole term, it's called the gain. So you had some voltage in. I said op amps are magical because they allow us to do math. In this case, this setup of an op amp allows us to multiply, and it multiplies by 1 plus RF over RN. We call that term here the gain. It's what we multiplied Vn by, gain it by something to get V out. It's not what you add to it, it's what you multiply by. Okay, so it is helpful to know that term. This is called a non-inverting amplifier setup. Why is that? Well, for one thing, my voltage N is directly connected to which input? This plus guy, what did we call that input? He had a name. Our non-inverting input, good. Okay, not our inverting one. Also, what happens to my output compared to my input? If, oh, again, for this example, I'll do that. For this example, we'll do this. Let's say if Vn, give an actual value to this voltage in source, is 5 volts, positive 5 volts. And I make RF over RN equal to 2, as we said down here, that it means he multiplies by 3. What do I get for V out? Yeah, 15, right? I take RF over RN, I add 1, that's 3. 3 times Vn, so 3 times 5 is 15. He's positive 15 volts, right? If this was positive 5 volts. He did not change sign, or he did not invert the sign. Again, it's like unsweetened tea, it's named by what he didn't do. You had a positive voltage at your input, you get a positive voltage at your output. If this becomes negative, if this was a negative voltage in, like you put in negative 5 volts, then you get negative 15 volts out. He did not invert or flip the sign from your input to your output. Questions or concerns over that setup of an op amp? Again, we derive that based on our op amp rules. I will tell you we will use this setup then a lot, as we'll see some other setups of op amps, in which case you can go back and look at these equations. But for other unknown op amp circuits, it is helpful to know the op amp rules of how we got to this point. How do we get V out equals Vn? We derive that from looking at current into our nodes, solving for V out. Let's look at another way we could hook up an op amp in a circuit. Here's my op amp here. Let's look at what we can do. What current is going to go through this resistor R here, or how can I calculate it? Good, we meant 0. Why? Because no current can go into or out of the inputs to my op amps. And this is one of my inputs. He's my non-inverting input. Did he have any other path to go? So he went through this resistor? Nope. So if he had no other place to go, he can't go in the op amp. He's nothing. What about this current through Rn? Does he have to be 0? Good, Binmit, that is actually correct. I could find that current by, he'd be Vn, in this case, over Rn from it. How am I going to get that? Look at this from it. So he's not necessarily 0, and he's actually not going to be 0. If this current is 0, my voltage down here is what? On this wire, what am I at down here? What did I call that voltage? Ground, or 0 volts, right? If I have no current through a resistor, so I is 0, what's your voltage drop across that resistor? What's delta V? Also 0. No current, no voltage drop across a resistor. It's not true for everything else. Like a voltage source can have a voltage, just do keep in mind, like I can have 5 volts, even if this is open, like an open circuit, and no current flowing through it. He's still 5-volt difference. That's just not true with a resistor with Ohm's law, right? If a resistor is going to an open circuit, but there's no current, then there's also no voltage drop. Okay? So if there's no voltage drop, what's my voltage right here? I'm going to call this one again, the top, VA. Call this one VB. What's my voltage at VB? Point VB. It does have to equal VA based on my op-amp rules. It wouldn't necessarily be I times Rn, because that would be my voltage drop over this resistor, starting at Vn to this point. But getting to this guy, if I have 0 current through here, which means I have 0 voltage drop. I start at 0 volts. Yeah, good, Michael. I changed no voltage because I dropped no voltage when I had no current through this resistor. He's also 0 volts. That makes sense? Was that true in this setup? No, right? The voltage at these inputs wasn't 0, current through them 0, but this voltage was equal to Vn, which again could have been 5 volts or 10 volts or whatever I make this voltage source. You just had to be the same as here. I have to be careful of how I hook it up. If I hook it up to ground, then that's 0 volts if he has no place to go. So if VB is 0 volts, what's VA? Also 0 volts. Why? Because the voltage at my inputs for op amps, if there's a feedback loop, has to be the same. Is there a feedback loop here? Yes. Good, Brianna. From V out to my inverting input, I have a path, in this case with a resistor RF. So these voltages have to be the same. They won't always be 0. They won't always be Vn. I've got to look at how my circuit is hooked up to do that. Okay. So now, knowing what VA is, he's 0 volts. This I didn't have to be 0, because where could he go? Once he goes through Rn, where is he going to go? Can't go into my op amp, so he can't go on this little itty bitty wire here, 0. Good, through RF. You can go up that way. I'm just going to say I is equal to I. Are we okay with that? Otherwise, he's technically nodal. You can call this I1 and this is I2, entering equals leaving. But very simple nodal equation otherwise from it. I'll label them. We'll call my I1 I2, just to be consistent. So how am I going to write I1? Again, I like my I's when I do nodal analysis to be written as fractions of delta V over R. I1 goes from what voltage to what voltage over what resistance? Yeah, so he goes from Vn on this side to, what's my voltage at VA? 0. Or you can just write V in here, but I like to always write the 0 so I know which way it is. Again, when we did it this way, with this circuit, then I started at 0, and so it made us have a negative sign. If I get lazy in that, then I can often miss my signs. So over Rn. How do I write I2 as delta V over R? Good. 0 to V out, because VA is 0, starts there, goes to V out over RF. And do make sure you're also putting the, this would be parentheses over the whole thing from it. I want to solve this for what is my voltage out in terms of my voltage in to find out what did this circuit do? What did it make at my voltage out of my op amp compared to what I put into it from a voltage in source? So how do I solve that? And multiply by RF on both sides. What do I get on my left-hand side? I multiply by RF over here. I'm going to take this term, multiply by RF. What do I get? I'm going to get RF now over Rn times Vn. Technically times Vn minus 0, but now I'm okay dropping the 0. Equals, what am I left with on this side? If all I did was multiply by RF, I'm left with negative V out. So do be careful. Again, that's why that sign mattered. That sucker. How do I get rid of the negative to just identify V out? Multiply by -1 on both sides. And I get negative RF over Rn times Vn equals V out. What did this circuit do? He took a voltage in and multiplied by what? Multiplied by negative the ratio of RF over Rn. So if I want V out to end up equaling -4 times Vn, what do you want RF over Rn to equal for this circuit? Four. And this one's even easier than the other one. I don't have a pesky +1. Now, if you want V out to equal 4, just 4 times Vn, can I do this with just this circuit? It's a little bit of a mental thought question for us. No, good. The ratio can't be negative. There's no such thing as negative resistance. Okay, so this guy's an inverting amplifier. Why? Because he takes a voltage in, and no matter what, he's going to invert or flip the sign compared to my output. If I start with positive 2 volts in, and I multiply by -4, I'll get -8 out. Flipped signs. Can this guy, similarly, going back to my non-inverting amplifier, can he multiply, let's say, by, I want V out to equal 0.5 times Vn. Can he do that? If so, what should I make RF over Rn to do that? If I want to get half my voltage in out, can I do this with this non-inverting amplifier? Yeah, the gain for this always has to be greater than 1, because if I can't have negative resistors, and there's no such thing as that, then the least I can do is 1 plus 0, but I can't even really get 0. Okay, so you can't multiply by something less than 1. Most of the time you want to make something bigger, like you have a voltage in, make it bigger, like more money, right? More voltage, more money. Most people like that. But if you do want to make something smaller, like to fit in a graph of a smaller scale, you can't do it with this guy. Okay, we will learn as a hint that I can use this amplifier and put it through another one at the end, and then I flip my sign twice, and that basically multiplies by -1 once and multiplies by -1 again, in which case you can use this one to multiply by a number less than 1, but just with one of them it's always negative. So I can, if I want, with here, V out to at least equal negative 0.5 times Vn. Can I do that? What do I want, RF? Give me values. Let's actually do values here. Give me values. It can be, you know, there are infinite possibilities here. What should RF be and what should RN be to do this with my inverting amplifier? Any values you want that make this work? Yeah, so if I have RF is 500 ohms, thanks Miriam, and I have RN is 1,000 ohms or a kilo ohm, then 500 over 1,000 is 0.5 or half. And he'll do that. It's just with the negative. Again, we'll learn if you want to get rid of the -2, you can put it through another one. A lot of the time, while we should note that it's negative, we don't care much about that. It's the magnitude or the absolute value that matters, in which case inverting amplifiers are really useful. And a lot of the time, again, you want to make them bigger, in which case non-inverting amplifiers are just fine. But if you want to make your signal smaller value, or you want to take Vn and make it smaller voltage, can't do that with a non-inverting amplifier. Okay, I'm actually going to stop here because I have a meeting to go to at 1 back again, but we will get into next week. We'll continue our op amps, learning a setup called an inverting summer that will allow us to add voltages together. Remember I said op amps can do math for us. We've learned how to multiply. In theory, multiplying by a number less than 1 is dividing, so this can divide as well. This one just can't divide. It can't multiply by a number less than 1. We'll learn how to add, and we'll learn how to subtract by hooking up our op amps in different circuits, using our op amp rules to analyze them. These 4 op amps, an inverting op amp, a non-inverting op amp, an inverting summer, which means I sum or add, and a difference amp, which means I take a difference between 2 voltages, allow us to do basic math, add, subtract, multiply, divide, anything we want. So we will use them a lot. And again, we'll get into the habit then of designing circuits to do the math we want, to multiply by what we want, to divide by what we want, to add what we want, to subtract what we want, which is really powerful for processing electrical signals or electrical data. It's how your computers do math too, is that there are things inside them that can do that. Okay, we will stop there and continue those next week. Lab, this week we'll do 7 in Norton. Don't forget you did get 2 extra days because I didn't have the recordings up for Mesh and Nodal, but do make sure you're writing that lab report because this one's a long one when it was 2 weeks of doing Mesh or Nodal analysis by computer or by hand. If you have questions on that, again, I got 5 minutes for things now. I'm happy to answer questions on those. Otherwise, have a great one and see you Tuesday or Wednesday.